Okay. Good afternoon and welcome. I'm Dr. Oskar Agets, and I'm the chairman of today's PhD defense. And it's a pleasure to introduce the respondent, Brian Thorsbro, who will defend his thesis work today. Brian has been supervised by Dr. Nils Ryde and co-supervised by Dr. Hampus Nilsson and Dr. Henrik Jönsson. The faculty opponent for this defense is Professor Katie Pilakovsky at the Department of Astronomy at Indiana University. She is joining us via Zoom. The members of the examination committee are Docent Magnus Axelsson, Institute for Astronomy, Stockholm University, Dr. Paula Di Matteo, Paris Observatory, and Dr. Alejandra Recio Blanco, Lagrange Laboratory, Nice Observatory. And the agenda of the defense will be as follows. I will begin by giving the respondent the opportunity to, if necessary, present an erratum pointing out printing errors and such matters in the thesis. And the opponent will then begin with a review of the research field pertaining to the thesis. This is followed by a presentation by the respondent on his thesis work. After these presentations, the actual defense will start, where the opponent will ask questions, discuss, and bring up critique of the thesis work, which the respondent will respond to. At the end of this dialogue, the opponent gets the opportunity to sum up her impressions of the thesis. I will then hand over to the examination committee for further questions. And once this is done, and when I'm satisfied, I will hand over to the audience for further questions. Participants joining us via the YouTube broadcast can submit questions using a tool called Menti. And I think we will have some information about this here. Is that correct? Let's see. Yes. So you should be able to see this screen now. So if you go to menti.com and enter this code, so please write this down. I will bring this up later in the defense, but write down this code. And when you enter it on the web page, you can write a question anonymously, and I will read it to Brian. Okay. Great. After these questions from the audience, I will close the defense, and the examination committee will meet in a closed meeting to discuss the outcome. Okay, so that is the agenda for today. So we will now begin. Okay, Brian, maybe you want to take the chair here or stand by the laptop. So first I will give you the opportunity to present an erratum. Is there such a thing for you?
I am not aware of any typos or corrections needed.
Okay.
Not saying there couldn't be any, but I'm not aware of any.
Okay, very good. Okay, then I will give the word to the opponent, Professor Pilakovsky. So please, whenever you are ready.
So I am unmuted, and let me share my screen. Let's see, do I have the option? Here we go. So I am here to begin with a review of the public defense for O'Brien's thesis, and I'm happy to do so. Hold on a second. This happened yesterday as well. There we go. Good. All right. So I would like to begin with a very brief review of the context of the thesis and understand its importance to the broader field of understanding the origin and evolution of our galaxy and of other galaxies. The thesis focuses on the nuclear star cluster at the center of the Milky Way. And this is a region that has been shrouded in dust and mystery because of the complex extinction that lies between us and the center of the Milky Way. This region is buried in what we would consider a red and dead bulge, a region of a limited or lacking star formation, primarily but not entirely old stars, but which holds about 20% of the mass of the Milky Way. What I'd like to do is to zero in from this larger picture, which covers some tens of degrees of galactic longitude and latitude, to what we see as we move in toward the galactic center, looking at a scale of around 1 degree. And that is, depending on what wavelength we look, we see very different things. If we look in X-rays, we see a very active region with bright X-ray sources, including the central black hole, likely other black holes, neutron stars, star clusters, young star clusters with massive stars, star-forming giant molecular clouds, a hot gas, and of course in the center, Sagittarius A star. If we look at radio wavelengths, we also see a very active region. There's a ring of cold, dense hydrogen that orbits around the galactic center that contains something like 30 million solar masses. So a very active region surrounding the nuclear star cluster. As we move in, we come to the nuclear stellar disk, which has a scale of a couple of hundred parsecs surrounding Sagittarius A star and the nuclear star cluster in the very center. The nuclear stellar disk is there. The nuclear star cluster has a radius of some maybe 5 to 10 parsecs, also contains a mass of around 30 solar masses, that it apparently is mostly old and massive stars. And as we zoom into the center of the Milky Way, through the nuclear bulge to the infrared image, and then zooming in toward the very center, we see emerging the nuclear star cluster that is the subject of this thesis. We know in this central region of the Milky Way, there are many young stars, particularly young massive stars. We see Wolf-Rayet stars and other emission line stars, stars that appear to be hot with featureless spectra, young stars of various types, O and B stars. These tend to lie within about half a parsec of the center of the Milky Way and appear to have very young ages, somewhere around 3 to 8 million years. It's likely they were formed in place, but their origin remains somewhat mysterious, as does the actual flow of gas that might come in that would be there to produce these stars. We know that nuclear star clusters are prominent in the centers of galaxies. They're particularly visible in the centers of low mass galaxies. They've become much larger or much more difficult to detect in the centers of massive galaxies like our Milky Way, but we anticipate that they're likely there. We don't find them so much in massive elliptical galaxies. Likely they are disrupted by merger events, but in spirals we certainly do. We know that for lower mass spiral galaxies and for lower mass elliptical galaxies, that there is a very large fraction of these galaxies that are identified as containing nuclear star clusters. Our Milky Way lies at the upper end of the region in which we can straightforwardly detect these in comparable mass galaxies. And so it's very difficult to determine in more massive spirals whether they contain these nuclear star clusters or not, or what percentage of massive spirals actually contain the nuclear star clusters. I should note that our own galaxy lies at a mass somewhere around here. And so it's right at the upper edge of where we can detect nuclear star clusters in other galaxies. So understanding the Milky Way's nuclear star cluster helps us understand galaxies in a very important way. And ours is the only one that we can really study in any detail whatsoever. We'd like to know, how did the nuclear star cluster form? What is its star formation history? Clearly there's ongoing star formation now. Clearly it contains old stars, but what is the general process of the renewal of this region? How did the stars get there? What is the history of that star formation? So when and where do those NSC stars form? And then what is the relationship between the bulge and the NSC? It's dynamically a very complex region with gas, cold gas, hot gas, lots of stars, lots of motion and activity. It's a very complicated region and one we really need to understand better. Critical questions that we'd like to understand are the metallicity and age distribution of the stars in the nuclear star cluster that will tell us about its origin and evolution in not only our galaxy, but give us clues about what's happening in other galaxies as well. So the relevance of this thesis work is that it provides a detailed study and several detailed studies of the compositions of stars in the NSC that give us information about the star formation history of this region of the Milky Way. These thesis papers are among the very first attempts to carry out high dispersion spectroscopy, which gives us more detailed abundances and gives us a lot more information about the nature of these stars in particular. And so the thesis papers are extremely important for that particular reason. The high dispersion analysis of these stars firmly established the importance of these old metal poor stars in the NSC, even though the integrated light is dominated by young, luminous, and massive stars. And these detailed abundances are critically important if we want to understand the history, the formation of the NSC. And the fifth paper in the thesis provides us this wonderful insight into the alpha to iron ratios, which we know tell us a lot about the nature of the formation of the elements that go into the NSC. I would like to go over a few of the highlights of each of the papers and then come to a final conclusion. So the first paper that was included in the thesis provides important infrastructure in particular for the future work that is included in the thesis. And I would really like to focus in these highlights, particularly on the contributions that Brian has made to these papers as we go forward, as those contributions increase later from the beginning papers to the later papers in the thesis. For this paper in particular, paper 1, there is an important development of the line list for the spectrum synthesis. This line list is important because it provides the fundamental data on which the conclusions are based. It's important to have an accurate line list, one that's reliable, one that's vetted against other stars whose compositions we know. And this was an important result of this paper to produce such a list. I've included one figure from the paper, and that is the spectrum, examples of lines from the paper showing the observed spectrum in black, the best fit model in red, and corresponding slightly different abundances showing in blue, the giving some hint of the uncertainties that one would have in measuring the abundances of these things. This paper also establishes this particular star, GC 10812, as a likely member of the nuclear stellar disk, and is also important in its own right as an ability to characterize the composition and origin of the nuclear stellar disk. It does produce a metal abundance, an iron abundance, and alpha element enhancement for this star, which indicates that formation of the elements likely coming from core collapse supernovae, but also the star is amongst the most metal poor found in this region of the galaxy. And so also provides kind of an important lower bound or estimate of what is the metal abundance in these low metallicity stars in these regions of the galaxy. This star in particular was identified as a member of the nuclear stellar disk, as not the nuclear stellar cluster itself, but the surrounding population that surrounds the nuclear stellar cluster. In the second paper that was led by Mike Rich in 2017, we see a larger sample of metallicities, again, analyzed by Brian very carefully and very appropriately. A sample of 17 M giants, predominantly members of the nuclear star cluster, but with a few members of the nuclear stellar disk included. This paper in particular, Brian was responsible for the analysis of the stars and deriving the metal abundances. And he found a very broad range of metallicities in the nuclear stellar disk, from about 1/10 solar to somewhat around 4 times solar metal abundance, with a median abundance of a little bit below solar amongst the 17 stars in these regions, in particular in the nuclear star cluster. This paper also included the formal development of the isochrone method for setting the surface gravities for the stars. And I've selected one figure from the paper here showing the stars that were observed and analyzed by Brian, plotted with an HR diagram with the Yanzai-Yale isochrones for a range of metallicities that you see from fairly metal rich to fairly metal poor, showing how the stars lie along these isochrones and providing an ability to get an independent measurement of the surface gravities, which are necessary for the analysis to derive appropriate abundances. And so this paper makes these two main contributions, that is the range of metallicities and a preliminary look at the metallicity distribution function in the nuclear stellar cluster, and also the formal development of the isochrone method for setting the surface gravities of these stars, which is very important given the temperatures and the spectra that they come to. In papers 3 and 4, Brian has attempted, or has actually taken a very striking result that was published about the abundance of scandium in stars in this region of the galaxy, and which purported to show extremely high scandium abundances, which really could not be explained by stellar evolution models in the production of elements. So the nucleosynthesis, the origin of this scandium was very unlikely, and yet published results showed extremely high, upwards of a factor of 10 in the scandium abundance above this relative to iron, relative to the disk and to other stars that had been observed in the bulge. Brian very capably looked at the spectra that he had of stars in the nuclear star cluster in the solar and the vicinity around there, and also got a sample of stars from the solar neighborhood to compare to, and clearly found evidence that similar effects are seen in M giants in the solar neighborhood as were observed in the center of the Milky Way, and was able to show quite effectively that this is not an effect of the abundance, but rather an effect in the line formation due to the very low temperatures of the stars. He was able to obtain hyperfine data for the scandium lines that were used and show the effect of hyperfine splitting on line strength, and also to investigate the non-LTE formation of these lines, and establish that this result that had been published was spurious. In the paper 4 of this series, he provided very strong advocacy for developing continued research in atomic physics to provide the kinds of data that astronomers need to really take advantage of the spectra that we can get and to understand the line formation, so that we can actually use many of the lines in the infrared part of the spectrum for abundance analysis. And that advocacy is important, remains important, and we hope that the atomic physicists will take note and continue to produce the data that we need. So those papers have an important goal of benefiting the entire field through both the careful analysis that Brian did, establishing the correct abundance of scandium in this region of the galaxy, and also to push people to get the data that we need. Paper 5 is actually my favorite of this whole series. In this paper, Brian accomplished several important goals. First of all, he developed a new method for the temperature determination in these very cool giants that I think will be very useful to others, particularly looking at the scandium line strength as an indicator of temperature, where the line strength is more affected by temperature than by many other factors, including abundance. He used this paper to update the metallicity distribution function for the stars in the NSC with a somewhat enlarged sample, set an upper limit to the abundance of stars found there, that stars did not seem to exceed about plus 0.5. That is a factor of 3 above solar in their proportion to iron, and also was able to include analysis of silicon in these NSC stars to obtain an alpha to Fe ratio for the NSC, which establishes something in more detail about their origin. In contributions to methodology overall, the thesis has produced a calibrated list of reliable spectral lines for use in the infrared part of the spectrum. These are lines that are unblended, have known atomic parameters, and have been vetted against stars of known composition to confirm their atomic parameters. He's developed techniques for determining stellar parameters, in particular temperatures for these M giants, and a method for determining their gravities, and also applied methodology very carefully for determining membership in the NSC as compared to the nuclear stellar disk, looking at the colors and reddenings of the stars in his samples. These are very important contributions to our understanding of the infrared spectrum, and we need the infrared spectrum in order to study stars in the nuclear star cluster. It's the only way that we can see them. In terms of the science produced, he's given us the first comprehensive study of the composition of the NSC with the preliminary metallicity distribution, peaking at an iron abundance of about minus 0.6 and indicating a fairly broad metallicity range from minus 1.2 to plus 0.5 for stars in the nuclear star cluster, and established that the metal poor population is actually the population in the NSC may appear somewhat more metal poor than the broader bulge population itself. I've included here a picture from a recent paper by Sitt and Ness looking at apogee data for bulge stars and comparing that to the disk, but also I've added a figure from Ryan's fifth paper showing the metallicity distribution function for the bulge and allowing comparison. And it appears that the NSC is in fact somewhat metal poor than we find for the disk or for the bulge overall. So these are important contributions to the to our understanding of the NSC. I want to also add that this dependence that he found on the silicon to iron ratio on metallicity suggests something interesting happening for the more metal rich stars in the NSC, but we certainly need a bigger sample and more elements to confirm this interesting result of a high silicon to iron ratio for the metal rich stars in the NSC. There's a lot to do for future work, and he's laid a wonderful foundation for continuing that work. I think that's what I have to say, so I'm going to stop sharing at this point.
Okay, thank you very much, Katie, for that introduction. I will now hand over to the respondent, Bernd Thorsbro, for an introduction to his thesis work. Okay.
Thank you. Thank you, Katie, for the very nice talk and the very nice presentation. There's a lot of good stuff in there. Can I get this Zoom? There we go. Yes, so I'm going to talk about my project in more detail, clues to galaxy evolution from spectroscopic observation of galactic center stars. And basically, I'm going to talk a little bit about more about how we did, what we did, and stuff like that. One important thing to consider, which Katie also pointed out to, is that observations at the galactic center are difficult. Here's one of my favorite illustrations of the Milky Way. We have the sun out here, and we have the galactic center in here. This is based on observations doing with the ESO Infrared Space Observatory. And in between, we can see there's a lot of stuff between the sun and the galactic center. And this stuff, dust, as it lies in the way, means that all the light coming in from the galactic center gets absorbed before it comes out to us. And this means that when we point a telescope to the galactic center, we are not really able to get any light in the normal visual range with an optical telescope. So instead, we have to turn to infrared. In infrared is less affected by the dust in the way. So actually, the infrared light from the galactic center, about 15–16% of it can penetrate out into our position. Can we turn off the sound on this one? Perfect. Thank you. And also the galactic center is, of course, 8.2, 8.3 kiloparsecs away from us. So we need to observe very bright stars. If we just look at a standard Gaia-Hertzsprung-Russell diagram of stars near us, we can see that on the y-axis, we have kind of the luminosity, the amount of light coming from the stars, and the temperature on the x-axis. So these stars that we are observing in the galactic center are here at the very top of the stars. So it's very, very bright stars we're looking at. These very bright stars we call M giants. And they are not that much observed here in astronomy. We usually like to observe these dwarf stars here on the main sequence because the sun is a dwarf star on the main sequence, so it's usually more interesting. And also we usually observe a bit warmer giant stars out here because in the optical range, M giants are very, very have very, very busy spectra with lots of molecular lines, which make them very difficult to observe. So, but when we go into the galactic center, we need very, very bright stars in the infrared, so we actually end up here on the top of the branch. If we look at the nuclear cluster, which Katie also pointed out to, we have actually, it's not very big. At the very center, we have this red number of stars density. It's only about these 4 or 5 parsecs in the radius, but still it contains almost 20 million solar masses, so there's really, really a lot of stars in there. If the Earth was placed there, we will have so many stars on our night sky that it will be kind of bright. And outside of the nuclear star cluster, we have the nuclear stellar disks. 1 degree here on the sky is about 140 parsecs at the galactic center. And the mass of the nuclear stellar disk is about 100 times the mass of the nuclear star cluster. So in the whole system of these two things together, actually nuclear stellar disk could also be very, very important to analyze. We are not the only collaboration that are looking into the stars of the galactic center. So I'll here bring up a bit work from another group that's also looking into this. It's Stu et al. And Feldmatter Krause et al. So they have been looking also at the metallicity range, although in the initial work they used very low resolution observations, and then they used machine learning to determine the stellar parameters. And the problem, so we see here is that this is the figure from the article, but if you look at the table of the article and plot all the stars, you see slightly similar image between these two. The problem was that some of the log Gs of the stars in this original work were about 4, which means it was dwarf stars, which we cannot observe. So there was definitely some work to do with the machine learning here. The machine learning has been improved and calibrated against the apogee stars. Still, the machine learning is calibrated on stars above 4,000 Kelvin, while usually the stars down here is between 3,000 and 4,000. So there is some extrapolation going on, but it's very clear that they also find very metal-rich stars. Interesting enough, they go up to 1 and beyond in metallicity, which is a very, very high number that, and as Katie showed, we don't get more than 0.5. It's a very high number, and you can discuss if it's really feasible to have stars with that high metallicities. For the audience that is not astronomers, metallicity is a kind of a pollution of elements heavier than helium and hydrogen. And as time goes on through stellar processes, this number increases. So in a way, it's very important also as some kind of time proxy and in stellar evolution theory to kind of see how much metallicity builds up over time. We compare this to globular clusters because a lot of theories on how the nuclear star cluster could have been formed has revolved around globular clusters being formed out in the Milky Way and then slowly spiraling in and getting absorbed into the center of the galaxy. But if we look at the globular clusters inside of 3 kiloparsecs from the center, we find that they are not as metal rich as the stars we found in the nuclear star cluster. So maybe they are not formed through infall of globular cluster, but maybe the nuclear star cluster has been formed some kind of in situ. And as Katie also explained, there are some young stars and other things. It's a very complex region in there, so it's not completely unlikely that we should look at the in situ formation scenario. Recently, the results posted here in September, preprint from their group, they examine these two scenarios in situ versus infall of globular clusters. And they find that there is a low metallicity group that has a more tight orbit and they're faster rotating, which they think dynamically could belong to this infall of globular clusters. So the idea now is that maybe we have a mix. That most of the stars in the galactic center are formed there, but we also have some kind of contributions of stars coming in. So our project, of course, is observing these stars. We do that with a telescope. And here is a 10-meter diameter telescope. This is a very big telescope over here that we point towards the galactic center. And it's big enough to capture the infrared light from the galactic center. It's placed on Hawaii. On Hawaii, it's far enough down towards the equator that on certain nights during the year, the galactic center comes up high enough to be observed. But otherwise, we will like to observe the galactic center from the southern hemisphere. The stars that we have observed are listed here. The blue circle you see is projected distance from the center, 2.5 parsecs. So all these stars, when we target them, were as close as possible to the galactic center. But of course, we cannot be completely sure if they're a bit behind or a bit in front. So we're trying to get stars as close to the galactic center as possible. But also we need to put a spectral slit on top of the star to observe it. So if we go too deep in, it becomes very, very crowded and very difficult to put on a slit on top to observe the light from the star. And that means that we like to stay a bit outside. So Keck has what they call adaptive optics, where you can improve the image quality. It means that you actually can go closer. Our collaborators actually have used that quite a bit. But this adaptive optics costs in photons, so it means that we have less, we capture less light, meaning we have to expose for a longer time, meaning we get fewer stars. So we kind of made this balance and stayed a bit outside the center, but still inside the nuclear star cluster. As you're going to see, some of them turns out to belong maybe more likely to the nuclear stellar disk. But even the dynamics people are discussing exactly, are they now belonging to the nuclear star cluster? Are they now belonging to the nuclear stellar disk? Sometimes the nuclear star cluster disk can come out a bit, and sometimes the nuclear stellar disk star can come in a bit and stuff like that. So that is actually still a bit debatable, but we have done our best to figure out the membership our stars have to either the nuclear star cluster or the nuclear stellar disk. The color magnitude diagram that Katie shown shows that, so here we are looking at the stars in different color magnitudes that we have done with the symphony. So this is kind of just like the diagram before with the Hasbro-Russell diagram. We try to map out the different light types, different types of star, and we try to be as varied as possible in this diagram. So we have all kinds of stars in our observation, trying to not fall into too much selection effects. The first star we observed was very metal poor, as Katie pointed out, and Katie showed the very, very nice spectra. So here I'm going to show the abundance plot instead. It was not planned, but and as you can see here we have different Christiansen stars in the background and some of our collaborators' earlier work for the bulge here in general. And up here in all four plots, we have this green star, which is our metal poor galactic center star. And in a sense, the conclusion from the first paper is also that this star is not that different from the other stars that we observe in our galaxy. So we're not using this star to say there is something special about the galactic center. In order to determine the stellar parameters, the temperatures and the surface gravity, we have to look into a different couple of methods. For the temperature, we used we looked at the spectras we have from Symphony, and there you have molecular CO features of the stars. And the amount of these CO features we have in the stars, we then use an empiric relation developed by Bloom et al. In 2003 and later refined by Schultheis et al. To get some temperatures. But in order to get the surface gravities, we had a problem because it's a very, very patchy region, so using photometry was not so easy. So we actually decided to go down this route with the isochrone method that Katie also pointed a bit to. And this method is nice because our targets we have selected are mainly old red giants. And these isochrones usually have an age dependent. But when we go into this old giant stuff, most of the isochrones overlap and age suddenly doesn't become a factor anymore for stars that are older than these 4 or 5 gigayears. That means that the variables we have left in this function is temperature, surface gravity, and metallicities. So we then developed an iterate process where we said, okay, what kind of, if we take the log G from the photometry, try to determine the metallicity, if it falls outside, we adjust it a bit and do this iteratively until we find a function that fits with the isochrone. We can actually use the isochrone as a constraint to find a proper surface gravity for these stars. So we have done that, and we also try to look into and validate it against apogee and other methods to become a bit certain, and we like this method. Here I present the metallicity distributions using both of the methods, photometry and the isochrone method, and it doesn't vary that much, so that's a good sign. Most of the stars kind of agreed with both methods, which is good because it should. And some of them diverged a bit, and that's probably because of the patchy extinction. So we went with the isochrone method as the final result. Now for paper 3 and 4, we had this. We went on after paper 2 to work on the alpha abundances, which was a long hard work. But meanwhile, while we were doing that, another paper appeared claiming there was a lot of scandium in the galactic center. So we kind of backtracked a bit and looked at it because we have seen these very strong scandium lines as well. But we didn't touch them because as spectroscopist people, we don't think that this very strong line is something that you should immediately throw yourself at and trust. There's so many features, so many things you have to consider when you meet these strong lines. Scandium is interesting because it's an odd set element with a strong nuclear spin. And the paper that came out, here's a figure from the paper, showing that if you take 2 observations of galactic center stars, which are here in black, and compare them to stars, to models in blue and orange, we find that in the blue model is kind of trying to be a solar-like model, and the orange model is like scandium of Dex 1. It also has, so as Katie said, that's 10 times the scandium. And on top of this, these stars actually have a somewhat higher metallicity. So in the end, it turns out that the orange line is actually 40 times the amount of scandium in the sun. But okay, if you compare to the blue one, it's 10 times. And this is a lot of scandium. And if you have this amount of scandium, and the paper also said vanadium and yttrium, then you will need to be able to explain how it came there. So we looked at our data, and because, as I said earlier, M giants have not been that much observed in the optic regime because of molecular line blanketing all over the spectra, we had to develop our method taking a control sample of local solar neighborhood star, local disk stars, we call them. So we actually looked at this control sample and compared it to our galactic center sample. And in our paper 3, we show here the figure where we compare them. So we have stars here on top of each other. Galactic center star, solar neighborhood star, galactic center star, and solar neighborhood, galactic center. And they are ordered for the coldest star in the top, and then we increase the temperature as we go down. And here on the left is the scandium line. And for the cold stars, we see a very, very strong scandium line. And as the temperature increases, the scandium line disappears. Of course, we think that it is, of course, linked to that scandium is getting ionized. So the neutral scandium is simply disappearing as we reach the 4,000 Kelvin and beyond. But still, it's interesting, why are these so strong in the cold region? Actually, we could have stopped our paper there because you see the strong features are already in the galactic center and the solar neighborhood. But since we are curious about the atomic physics, we went a bit deeper into this to see how can it be they are so strong for the cold stars. If you look at the atomic physics for a moment, you can see that in the infrared, we have here marked with red some of the lines that happens, and these are energy diagrams for scandium and iron. And for the scandium line in the infrared region, where we're looking 2.3 microns, the line is very, very low in the energy diagram. And it's a metastable line, meaning that it has a high electron population. So in that sense alone, we have a lot of electrons that can interact with the light. So that's already one reason to why we would have a strong line. The other reason is that we have one 4s electron. And as I said earlier, this is a odd set atom, so it could be it has a strong nuclear spin. So there can be some, and yes, electrons has a tendency to go into the nucleus of the atom. So that could also maybe be a reason to think that there could be a strong hyperfine structure there. If we look at stars like Arcturus, which we have spectra from in very, very, very high resolution, and then look at this line we're looking at, we can see that in Arcturus, we don't have a one line, but rather a plateau. So together with the atomic physics in Lund and Malmö, we went down to the Italy laboratory and measured both the hyperfine structure and also the oscillator strengths. Master student Felix van Deling mentioned measured the hyperfine structure, and previous PhD student here at the observatory measured the oscillator strength, Ashley Pelle van Rudin. And together with their results, we were actually able to measure out the hyperfine structure and the strength of it, so we could start using the atomic data. Because when you just find one line in the database, it's of course not. It's an example of how the infrared database in atomic physics is not updated as it should be, which is also why we ended up doing this advocacy in paper 4. If we use this new information to model the strength of the line, and here on the y-axis we have the strength of the line, we can see as we go down in colder temperatures, the strength of the line, was we just used the one line originally in the database, doesn't become very strong. But if we add the hyperfine data, we find that we can actually model the line to be much stronger than it is. So in a sense, this is part of the explanation. And we then use this to see if we can measure the abundances. And for the warmer stars, it went okay, but for the colder stars, it was still not very good. In the background here, we are comparing to 2 other studies, K-Giants by Lomeva et al. 2018, and Disk Dwarfs by Battistini and Bensby from 2015. And both of those studies are using scandium-2, because those are harder stars, and by that time, the scandium, neutral scandium is gone, and you're using the first ionized scandium instead. If we plot the abundances versus temperature, we get a result that could indicate that scandium abundance is depending on temperature, which of course we don't think it is. So there's probably still more to be figured out with the scandium. There's probably some non-local thermodynamic equilibrium conditions and stuff. When you have very strong lines, you can have that kind of problems. So we caution against using scandium as abundance determination, at least for the cold stars. But the thing we really wanted to do was getting the alpha abundances. So we went back to our silicon. We have some good silicon lines in the infrared spectra that we like to investigate. They don't have all these hyperfine structures. It's an even set element and so on. But the other problem we had with our spectra is that they're cold stars. So there's a lot of molecules in these spectra. So here we have plotted some CN features from all of our stars on top of each other. In red are the CN features from the galactic center stars, and in blue are the CN features from the solar neighborhood stars. And as you can see, the stars are very, very busy with the molecules. In general, the galactic center stars are a bit colder than the solar neighborhood stars, just a tiny bit, which could explain why there is more CN in the galactic center stars. But actually, it could also be that there is something to examine even further, which we are thinking about. We tried to figure out how we can analyze the stars and get good abundances. And of course, because there's a lot of these molecules, we need to figure out if we can isolate good iron and silicon lines in our spectra. So what we do is we take we got some updated good molecular line lists from Chris Needon et al. And try to model if we change the CNN abundances a bit on these spectra, where do we see the spectra change? And then we find places here where iron doesn't change and here silicon doesn't change. So it seems like these two lines are free of so-called blends. So if we don't manage to get the CN modeling completely correct, we will still be able to use iron for iron abundance and silicon for silicon abundances. And we use this for a couple of lines. Of course, when we look at the galactic center and just look at the spectra for these two lines, we actually see that, interestingly enough, so for the iron lines, it looks fairly like similar. So this is the very metal-rich sample of our stars, like the 6 most metal-rich stars we are looking at and comparing them. And we can see that for this metal-rich group, the iron lines is kind of similar. But for some reason, the silicon line seems to stick out a bit. So this is something that that Katie also showed a bit on one of the plots, and I'll come back to soon. But for the iron line, we use that to update our metallicity distribution. And we have the black was the one we posted in 2017, and the red is the new and updated one. We also added 3 stars since then, so there's 3 more stars there. And in a sense, we're kind of getting the same metallicity distribution that we got first, but it could seem to be a bimodality, though the numbers are low, so we'll be careful about claiming that too much. But it will be interesting to see if we add more stars, whether or not that's going to turn out to be a real signal. If we look at the silicon versus iron abundances, we see that there is, in our case, this slightly enhanced silicon for the metal-rich stars. Just for comparison to the bulge, we can see that the blue stars and the not-so-metal-rich star seems to kind of fit along with the other results known from literature. But here we might have something that sticks out a bit. And we are, of course, curious to whether or not that turns out to be a real thing. At least it's a very, very strong indicator that we need to examine this further. We tried to collaborate with, we did collaborate with the chemical evolution models, and we tried to make some models to see if we can explain this. One model could be that maybe we have a star formation going on in the center of the galaxy, and then at some point, the gas that is created, that creates these stars, is renewed by some new gas that falls in. And when that happens, so here we have the abundance and the metallicity of the gas the stars are created from, and it develops over time. But then if some primordial gas with low metallicity comes in, it will reduce the metallicity of the gas, but it will also increase the density, and maybe it will start a new star formation or even star burst. Some people in the literature have suggested this could be the case for the galactic center. And we tried to model that a bit, and it could mean that it could be a scenario. We do not expect to find stars everywhere along this track, because at some point star formation is not happening. There could be a low density in the gas or some other effects, but the track goes through the populations we observe. Another model we tried was that imagine that there could be a stop in the star formation for some reason. Ditch, balding, the bar formation, AGN feedback happening for a period. I'm not really sure what will be the exact reason, but if we imagine there were a stop in the star formation, we could also, to some extent, replicate the signal. This, of course, needs to be examined further, but the nice things with these chemical evolution model is that it gives an entry to try to understand what these things could mean. And as you go deeper into these models, you might find even more things and suggestions for what to look for. In the future, we could imagine, so we like atomic physics, and we can imagine doing some more of this, like scandium with the yttrium, which is just below scandium in the periodic table and have many of similar features. And yttrium was also one of these elements that was claimed to have extremely large abundances, so it probably has many of the same issues going on. Lanthanum, that is below yttrium in the periodic table, and then of course vanadium, because that was the third element discussed in the other paper. So that's something we look into. We actually have yttrium measurements from a previous student, so that might be something that's actually going to happen soon. Stay tuned. Another thing we're looking into is these so-called young stars in the nuclear star cluster. And here is a plot from Nishiyama. Ooh, I don't remember if it's 1 parsec for the blue line. I can't remember. But they have looked in a lot of blue lines, and we actually have observed 3 of them. So we're looking into those. They are more massive, young, and could be interesting to see how young they are, and to discuss this formation of new stars going on in the region and stuff. So those are things we're working on at the moment. With that, I will say thank you.
Thank you, Brian. We will now move to the actual defense part of the Thesis Defense Act. That means that I believe it's best if you have a seat here, Brian, and I think we will have Katie asking questions. Is that correct? Yeah, so is it best if Brian sits in the chair? Yeah? Yeah, okay. All right, okay, and Katie, you're with us?
I just moved to... Should I just take the laptop down?
Yes, I am. I'm here.
Great. All right. Okay. So whenever you're ready, yeah, please start asking questions to Brian. Right?
2 seconds. 2 seconds. Getting the technique here. There we go.
Kavi?
Oh, I can see you. Hello, Katie.
Hello. Good to see you. These pictures are so tiny, and we may want to go to some of your slides as well, just in case there are things that you would like to show from.
I have a laptop in front of me with my slides and also a PDF of the thesis. If you have any points you want to jump to in the thesis.
I suspect we're all sitting here with copies of the thesis in our laps. All right, so let us start with the general picture. Based on what you've learned so far about the NSC and its composition and the ages of the stars, how can you help us put the Milky Way's NSC into the context of what we know in the larger view of the NSCs in other, particularly in spiral galaxies?
Yeah, so we have an NSC in the Milky Way exactly in the same way as we have it in most other galaxies. I think if you look at spiral galaxies themselves, there seems to be quite a linear relationship between the mass of the nuclear star cluster and the mass of the galaxy, and I think that and the Milky Way matches that. That picture, and I think, yeah, I'm not sure how many anyone actually knows, but I think it is a good signal that it could be co-evolved together. The whole, so then, I would think somewhere. I think that the nuclear star cluster somehow was created in situ together along with the rest of the galaxy as it formed. I don't think it has come in later or something like that. I think it's formed together with the galaxy. So many of these simulations that starts off with a big molecular gas cloud and collapse it to a galaxy, I think it's reasonable, the approach to that.
Okay, so our Milky Way has this boxy peanut view sense that seems. I'm not a galaxies person, but I understand that there are 2 types of bulges: the sort of spherical or spheroidal bulge and a boxy peanut shape. And we have a boxy peanut shape.
Yes.
Are there differences that we know of in the nuclear star clusters in those two different types of galaxies?
Not that I've heard of.
Okay.
I might have missed, but no, I don't. I'm not sure if they are connected. No. So it could be interesting if the formation of the bulge has an imprint on the nuclear star cluster. That could be interesting to examine, I think. I'm not sure it will have an imprint on the nuclear star cluster, actually, but that will be interesting, I think, to examine.
Since this is the one we still don't understand, but it's the one we understand the best.
I mean, if it's an external factor that's determining whether we get a boxy peanut or spherical bulge, it shouldn't be seen in the nuclear star cluster, but maybe there is a signal in the nuclear star cluster, and then that will actually put constraints to how the bulge is formed. So that will be interesting to figure out.
Yes, I think there's a lot we don't know and a lot we will learn, and it's a really exciting and interesting field. So let us talk specifically about some of the individual papers.
Okay.
So when I looked at your results for paper 1, where you were able to do several different elements in addition to iron,
Yes.
you found sort of similar excesses within the uncertainties of the measurements. The excesses of the other alpha elements seem to be about the same as
Yes.
and this is I guess one of the warmest stars in the sample, if I remember.
Yeah, it is.
Likely
so
because of its
metal poor, so there's not so much molecular contamination. So that's also why we did it first, because it was easy. So we also did the other alpha elements of that. We have looked at the other alpha elements in the other stars as well, but we're really worried about the CN blending, and some of the magnesium lines are very close to some telluric clustering. So we have, for many of the stars, simply not, we don't really think we can extract magnesium. We have thought about maybe doing, extracting some of the alphas for whatever subset we can extract them for. That's something we're thinking about. And also we are working with Ani Shamashi from the Galar survey people, and so they are doing NLT calculations for their stars, and we have somehow kind of managed to convince them to extend the temperature range down to 3000 Kelvin for the NLT calculations, and they are providing some very beautiful grid calculations for that. And maybe with those, we will be able to be better able to do the abundance analysis of these alpha elements. So that's something we're very optimistic.
Oh, sorry.
Sorry. That's something we're very optimistic about.
Given you have both the CO and the CN in your infrared spectra, do you see an opportunity for getting carbon and nitrogen and oxygen abundances from those? Or clearly you do the synthesis of the CN. So
yes, so we do try to model them in our stars, of course, so we can get a handle on the CN blends. Some of our lines actually have a little CN blend, so we also use that as a sanity check when we. So some of the silicon lines we think are unblended, and some have a little blend. So we also use that in our silicon analysis to get some kind of sanity check on our CN modeling. But what we really want to have is OH lines. There are a few, but they're very weak. So for most of the stars, it mostly become a limit instead of an abundance, an upper limit for we can set. And we will really like a little more resolution to get this better. There are so many degeneracies in these modelings that you can kind of go back and forth on many knots, and then then you become unsure if it's this knot you should be turning or this knot you should be turning. What we do think is that we have somewhat nitrogen over high abundance in the galactic center stars. And that could be an interesting result in itself, but we're not yet at a point where we say we can claim it. So it's but it looks like there could be a thing there to go for. So that's something we are looking into.
In the figure that you showed on, I don't remember if it was iron or silicon. I think it was the silicon one, where you picked the metal-rich stars and overplotted the spectra
Yes.
with the silicon and the CN. And there seemed to be, in both, I guess in both iron and silicon, there seemed to be a large, a range in the CN abundances that were in those stars. Would you suggest from those data that there might be, I think it was a double panel one that came later, although I can't remember for sure. Would you suggest there might be a nitrogen to iron variation at a given metallicity in the sample?
So I'm not sure that this nitrogen overabundance is. I don't have a strong feeling that it's only for the metal rich. Rather, I get the feeling that it's for all of them. And I try to see if I can. So in general, is this viewable? So in general, the galactic center stars are a bit colder than on average than the solar neighborhood stars. And if we try to take that into account, just to think that maybe there will be more CN features because they're colder, we still get a fairly large temperature difference needed to explain why they should be so much bigger, these features.
Mm-hmm.
And we don't have that as large temperature difference as we think is needed. So that's kind of a reason to think that there might be some nitrogen enhancement going on in the nuclear star cluster. Okay. So I think it could be an interesting result if it turns out that the light elements are more abundant in general in the nuclear star cluster.
So I was actually thinking more about figure 6, I think in paper 5.
Okay. I'll go to that one.
I think you showed us.
The computer here is thinking. Yes, this is not the right window. Stop share. I think I need to open the PDF. This is not my computer. I don't think the PDF is open. So we need to go to the desktop. There we are. Good. It opens it in Edge. Okay.
PDFs can sneak in anywhere.
Yeah. Okay, perfect. So I will go down to
this is page 7 of that paper.
Yeah.
Yes.
This one. Yeah.
Yeah. So this is what I was thinking of, where the iron looks pretty consistent amongst all of those stars, and yet there's a large variation in the strength of those CN features.
Yeah. So that's temperature also.
You think it is temperature? Okay.
Also, yeah, for sure. But it's the CN are in general stronger in the galactic center stars, which we saw on the other plot I showed you, and it's the same we're seeing here. Okay. And I'm not sure why this one goes crazy, but sometimes they do that in your spectras.
Yeah. So it would be interesting to take pairs of stars with similar temperatures and look at the CN strength in pairs of stars at similar temperature.
Yes.
Sample and see if in fact you see differences in CN that would indicate a variation in this, in the likely variation in the nitrogen abundance.
Yes. Yeah, I think the whole, I really like the CNO and try to find the abundances of these. I think these light elements are very, very important. Also because in the end, you will need to have a firm grasp on the molecules. And the light elements are key to this. So it will be really nice to get a much better understanding of CN, CO, and hopefully get some OH lines.
Yes, it really will be.
And it's I asked the Galar survey the same question. We don't have nitrogen. Okay, maybe in the future.
Someday, yeah.
I think it's something that will be. I think there could be a lot more focus on these light elements. Will be nice.
Given how prevalent these molecules are in the spectrum, I think it will be
exactly
useful and interesting to pursue them. Thinking back just about paper 1 at this point, which you worked on a few years ago. Given what you've learned since paper 1 was written, what would you do differently at this, if you were to go back and redo paper 1? Is there anything you would change?
So I actually did read at the star for this analysis.
Yes.
Yes. Because I want to make sure that it was up to date with the same analysis. So since paper 1, we have a much better understanding of the lines and the molecules than we had back then. Of course, in the very warm metal poor star, the molecular blending is not so much a problem. But still, so if you look at the result in paper 5 versus paper 1, it's not that different. They are all about the same inside the uncertainties. So I will definitely use my updated knowledge if I should do. I did the star one more time. So in a sense, I did go back and redo it with this updated.
And got the same answer pretty much.
Yeah, pretty much. But it is warm and it is featureless, so it's not so unexpected either.
Featureless, yes, right.
Compared to what we're seeing in the other stars.
Okay, all righty. In general, in your line list, that I think it was slightly different from paper 1 to paper 5. And surely because of temperature, I'm sure that has some difference. But can you describe the iron lines that went into the analysis? What is the range of excitation potential that you had? Were there a lot of differences amongst the different iron lines that you used? And sort of, is the list of the paper the complete set that you?
Yes, this is the complete line list we're using. So some of the iron lines, so they're usually the same kind of excitation potentials for these lines out in the K-band, pretty similar region in the energy diagram. Mostly the biggest concern we had was blending with other things. So that's the biggest concern we had between the first and the last paper. Particularly because when we try to model the CN lines, we see that some of the iron lines changes. So in a sense, suddenly the way we model the molecules affects how the different, some of the iron lines. So definitely there seems to be some blends included in those that one needs to have a handle on before you can use those iron lines. So these lines here were the one we ended up with to be the least blended.
And you have a range of about 3 eV.
Yes.
Did you, I guess just one line at 6.2 would be a lot to pin a whole analysis on, but are these lines consistent in the sense of confirming the temperatures that you adopted?
So we didn't do that.
Okay.
We didn't do that analysis. We stayed with the CO bandhead. And then we actually also did, I didn't say that during my talk, but we also used the scandium temperatures. As you can see here in table 3. So since the scandium was so temperature dependent, we thought, why not try to kind of use the same thinking of the CO bandhead for the scandium features. And it turned out that it actually was quite similar in most cases between those two stars. Not two stars, two sets, two different ways of doing temperature determinations. So actually that was quite comforting to see. And it's also a bit in my back head that maybe that's something that could be fine-tuned even more. If we can find some stars with proper stellar, what do you call it? Where you have very, very good temperatures because the stars diameters and stuff very good for stellar seismology, and use some very cold stars that have these seismology checks on the temperature, and use those as a blueprint for defining this method, and then try it again and see how it matches. And that could be very interesting to do. That's in the
Betelgeuse might be a good place to start.
Yeah, that's on the to-do list. That's on the to-do list.
I actually looked in detail at the temperature determinations in paper 5, and when the average difference between the symphony temperatures and the scandium temperatures that you got was about 120 Kelvin. So it was a systematic difference between the two.
Not that I can see.
And then the difference actually seemed to increase with temperature, so or with cooler temperatures. So the difference was smaller at lower temperature, but up to 400 degrees at the higher temperature.
Yeah, that's interesting.
There was a systematic variation between the two methods, and it depended on temperature. So I was kind of excited to use the average.
Yeah, I think it's also because the scandium feature starts to disappear at the higher temperature, so it becomes more difficult actually to use this method.
More uncertain at the higher temperature.
Yeah. We are more temperature dependent at the lower temperatures.
Okay. Yeah. No, that makes sense, I think. Going back to paper 2, when you use the isochrones. I'm sorry for jumping around so much.
No.
We will. When you use the isochrones, we know in stars that there is a change in the carbon abundance and a change in nitrogen abundance along the giant branch at the carbon isotope ratio is changing. Things change along the giant branch. Can you describe the models that you used for the isochrones in particular, that you used for establishing the gravities, and how those effects were accounted for in the models, and what the implications of those changes and differences would be on the stars themselves? So sort of what carbon abundance did these models have, and how do those models account for those changing abundances as the stars?
So we made a grid of calculations. So I took a range of carbon abundances and a range of nitrogen abundances. And for this grid, I then, for these ranges and for metallicity ranges, so we fixed the temperatures. So these values we have determined. So that's kind of one parameter space. One dimension we can reduce into parameter space. But then we made a grid calculation on the C and the N and the temperature, not temperature, and the metallicities. And with the metallicity and the temperature through the isochrones, we then got the log G. And together with this grid of C and N, we then calculated spectras, brute force for all the parameter space. And then we went in and compared this grid to the observed spectra to see if we can kind of find a spot where it minimized.
Yes, but I'm specifically asking about the isochrones themselves.
Yes. So we just
the isochrones.
Yeah, so we kind of went with a bulge-like alpha profile.
Okay, so
for
the alphas
the,
and the carbon were sort of a bulge-like composition
yeah.
for the isochrones.
Yeah.
Okay.
We kind of expect, so yeah, it was a starting point.
So the alphas in particular, because of the ionization potentials, are an important source of electrons.
Mm-hmm.
And also a source of capacity. And
Yeah, so we tried
on the isochrones. And you feel that was done.
So I actually tried so I tried to include, for instance, magnesium as a special dimension at some point, and silicon. And magnesium is maybe the primary electron donor, and try to vary these the magnesium abundance quite a bit in the grid calculations, and it didn't really seem to affect it that much. There was some small effects, but it seems to be insignificant compared to the other factors. So in a sense, I kind of said, okay, we don't have to worry too much about the magnesium ±2 dex. Doesn't really matter that much compared to getting the other things right. CNN was more important, actually. So in that sense, we don't feel too worried about the electron donation from the alpha elements.
Okay, good to hear. One of the things I've always wondered about is whether it's possible to determine the microturbulence from the CO lines when there's a range of line strength for the CO, uniform abundance. Is that something you have looked at or have thought about?
No, we haven't. We used results from Smith et al. And his microturbulence empirical examinations of giants, and kind of incorporated into our grid calculations and used that as a rule of thumb for our microturbulence. So we did, of course, we eyeballed the spectra themselves and checked that doesn't look weird, and we didn't really get a sense that this was something off-putting. We think that was a good result to use for our analysis.
Yeah, no, I'm pretty sure it's absolutely correct. I'm just curious whether there might be alternatives that you could get from the spectra themselves, and whether the CO lines, given that there is a significant range of strength, whether they might be appropriate.
That could be interesting. I mean, there are so many parameters you could turn on this. So yeah, that's a challenge we have.
It is a challenge, and the more ways that we can get at those parameters,
exactly.
Often it's helpful. I appreciated from all of these papers that different approaches to temperature that you were able to make use of and to confirm, to validate the values that you used. And for gravity and for microturbulence, that's a little more challenging. So I'm always looking for methods that would allow a confirmation.
We really, really would like to have some very good, strong signal, high resolution K-band spectra to see if we can get some really reliable log-G determination directly out of the spectra. That will be really nice. It's on our wish list.
Always, yeah. That wish list gets longer and longer.
Yeah, it does.
You had some discussion in a couple of the papers about the log W over lambda values of around, I think, 300 milliangstroms or so that you felt were sort of the upper limit of line strengths that you were able to use. How often did you ever have to fudge that a little bit and go to stronger lines?
Yeah, a little.
Okay.
So we use the stronger lines as well because it's nice that the weak lines list, and then we'd go over and look how does the strong line looks like. And in general, of course, they usually come out the same way as the weak lines. Sometimes you can have issues with the core of the spectral line, but that's okay for the strong lines. So we kind of lean on the strong lines and check them as well after we've seen the result with the weak lines, because we don't want the strong lines to be completely off either. But for the actual results, we don't really use them. It's more like we do our own sanity check with them on the side.
No, I know I'm often very tempted to use one of those stronger lines just because it's easy to measure because it's nice and strong, but also because often I don't have a choice. If I really want to get a particular species, there may not be a lot of options.
Yeah, so we have some very strong calcium lines and stuff like that. So we might come out with that when we have our NLT grid in place and stuff. But also, as we saw with the scandium, if you go out with too much, you have to be careful with these strong lines.
Oh, yes. Oh, yes. Looking a little bit more at paper 3 with the scandium, I noted that this Smith et al. Folks used the scandium line at 4.3 microns. And their stars may have been warmer. I didn't check that, but they did not see in their paper an enhancement of the scandium. Is it because of temperature, or is there something different about the LMC?
I don't know if the LMC has a scandium feature. Maybe it has.
Oh, I did see their coolest giant in their sample is 3,600 degrees.
Yeah, so they don't go as low as we do, but if they go too much above 4,000, they wouldn't have a line. It's been a while since I looked at that paper. So I can't remember exactly what they did.
Okay. Oh, they didn't find an enhancement. So at a temperature of 3,600. I was wondering if they should have found an enhancement of scandium.
No, I think they were just sufficiently warm to not be really in the critical problem area.
Okay. In paper 3, there's a note in the conclusion section. I think it is. I think I made a note of it somewhere. Where's paper 3? Somewhere I saw a little note that indicated that you thought some of the stars might be AGB instead of RGB. And now, of course, I can't find that little note. Oh, yeah. In the conclusions in paper 3, I think it's the third paragraph down. Cool giants we have analyzed are almost certainly on the asymptotic giant branch, and as such are likely to be the most luminous stars in their stellar population. Are they AGB stars or RGB stars? As you use the isochrone method, you're basically relying on, for the gravities, basically relying on the stars being on the RGB. And yet it's sometimes hard to tell which they are. Can you speak a little bit about that distinction, what it might mean for the spectrum, might mean for the results, and what you think they really are?
Yes, I'm not really sure what they really are, RGB or AGB. It also so that's something. If you would like to have the carbon in greater detail, C12, C13 ratios, to see if you have another dredge up going on, and that will be. I mean, we're not able to determine these ratios with the spectral ranges we have. We'd like to have, if we're going to have the band heads from the CO from both 12 and 13. And examine them together, it will be interesting, but we don't have that. So we're not really 100% sure. That's another problem to look into.
Yeah, so
it's trying the grid calculations to vary between the two. Yeah. So we did both grid calculation, assuming we had ratio 4 versus ratio 20 of the 12 to 13 ratio abundance, and it was minuscule difference in the spectral modeling that came out of it. So actually, in that sense, we didn't investigate that much further because it didn't really seem to impact our result in any significant way. No.
Just in evolutionary timescales, can you make a guess at what fraction of the stars might be AGB and what fraction might be RGB?
That's a good question. I don't know.
Yeah, it's when I think about at a metallicity of -1 or -0.5 or something like 47 tuck red giant branch, and think about just the relative numbers that when we have really good precision in the photometry, able to really assign stars on the AGB. My guess, just thinking about those color magnitude diagrams, my guess would likely be maybe a quarter or a third of the stars might be actually AGB.
It's possible.
Did you mentioned a second ago about the carbon-13 and trying to get the ratio. So did I hear what you said, that the carbon-13 CO bandhead is not within the spectral coverage you have?
No. And that's a pity. That's a pity. Yeah. So yeah, in the grid model, we try to assume one or the other, but we don't. It will be really nice. So the spectrums we have are cut, so it's cross dispersed. So we have a couple of ranges, and we spend a lot of time trying to figure out which lines we could put into those ranges, and also which continuum points we could put into these ranges, because the continuum points are, without the continuum points, you don't have anything to anchor on. So we ended up with that, and at that time we didn't think so much about T12, T13. So the bandhead is not included.
That makes sense. And also, if you're looking at lines that are accessible, you're probably going to avoid as much as you can the regions with CO in them.
Actually,
yeah,
we're actually happy we have the second CO bandhead, so that not the primary but the second. So that's something we have been a little. There was a study out with the CO bandhead temperatures for the second bandhead last winter. I tried to run it through, but that was a mistake in the paper.
okay.
I haven't looked further into it.
Are there any sodium lines within the spectral region that you have? And did they look odd? It's an odd low excitation potential element, and one that matters a lot in understanding globular cluster origins, and possibly could have implications in the bulge as well.
Did we have one sodium line very, very strong? Can't remember actually. I have to look at the spectra. We didn't have anything we thought this should be analyzed.
It would be fun to see. I know that there are a handful of sodium lines scattered throughout the region, but there may not have been any within the regions that you had access to. So the paper 3, and I think maybe also a little bit in paper 5, when you look at the silicon, talk somewhat about other alpha elements and whether they could whether you have access to results from those elements. And you very clearly laid out the need for better atomic data, particularly hyperfine and NLTE calculations, for magnesium, for calcium.
Yeah, so we have magnesium and calcium in the spectras, but the magnesium is very close to telluric clustering, and the calciums are very strong. So we attempted to make a calcium abundance out of the strong lines, but we want to be a little careful also.
Given the disk spectra that you have at comparable temperatures, would it have been possible to compare the calcium features in the bulge to nearby whatever other lines there are, and also in the disk stars, and see if there might be differences?
Well, I haven't done that. I should do that. Yes, good idea.
You have such a wonderful data set. There's so many questions I could ask.
Yes.
That come from the data set that are future work that you can do. I'm talking about.
I think that's a clear one to do, yes.
fascinating stuff. I really.
Yes, I'm noting it down here somewhere.
Let's see. So let's talk a little bit about the metallicity distribution function. And you've been very cautious, I think, about the limited number of stars, the small size of the sample. And it gives these interesting hints about a bimodal distribution.
Yes, it does. It's interesting because how did that occur?
Mm-hmm. We really want to know, right?
Yeah.
And that's both the frustration and the beauty of astronomy, that we really want to know, and it's really hard to get an answer.
And why are the this low metallicity group so similar between the two groups, and here it's so different?
Yes,
that's really interesting.
it is.
And yeah.
And yet such a small number of stars. I know this
exactly.
It's the best we can do, but boy, it's really tantalizing. Looking just at the iron distribution, it remains a small number of stars. So you have 3 or 4 at the peak, right? Tiny numbers. Could you describe what kinds of statistical tests you did? Obviously, you fit the Gaussian to both of those distributions, the one from paper 2 and the one from paper 5.
Oh, it's
uncertainties do you have to put on those fitted distributions to the stars, and how reliable do you feel the 2-component model is?
I wouldn't say it's too reliable. So we have 0.15 conservative uncertainty and the metallicity. We would like to claim 0.1, but we'll stay with 0.15 because of also all these temperatures and stuff going into it. So I'm not ready to put my head on the block for a bimodal distribution on this at all. We did a kernel density map for the statistics. It comes out this way, but I think it's more illustrative of it's a possible bimodality than an actual signal, I would say.
So there are statistical techniques that give you sort of a quantitative sense of what is the probability of a bimodal distribution.
Yeah.
The Markov chain, Monte Carlo sorts of approaches where you run many distributions by introducing scatter in the measurements based on the uncertainty of individual measurements, and can come out with a sort of a probability of whether there is a bimodal distribution or it really is just a single distribution. Have you thought about approaching this with that kind of an analysis?
Thought a little about it, but haven't done it. I was like, let's do the alpha and jump that.
Alphas are good.
It's only 20 stars, so I think that going. If you do too much statistics, I think it also, when the statistics becomes too complicated, I start to trust it less. If you can't do it with a symbol, I like when it's simple.
When it's simple and really obvious, it would be nice, wouldn't it? When I look at the bulge metallicity distributions, just for the bulge in general, they seem to be coming out with these really complicated metallicity distributions. Some 4 or 5 different peaks. And it scares me a lot. I just wish big samples are so important, but they're so hard to get in specific spectral cases. Future surveys will be invaluable, I think, in the spectroscopic surveys in particular, in trying to.
So one thing I'm thinking with these kind of examinations here is that in the future, someone will do machine learning and statistics and stuff like that. But all these fancy methods are dependent on the right learning set. But somehow someone has to figure out what learning set to use. And this is where we need this high resolution spectroscopy with deep manual analysis of the stars, saying, over in this region, we need to have these signals. They need to be embedded into the learning sets. Otherwise, your machine learning is not going to pick out the right signals when they do this big analysis of the survey data. So I kind of more see my role as trying to help define good learning sets for these systems, in a sense. And that's why we would like to push for higher resolution and high signal to noise and good atomic data and all that stuff, trying to do this nitty gritty as good as possible. And then go say, okay, machine learning is wonderful. Here's the signal you should look for.
I think that makes terrific sense. And I have to say, Lund is well known for being really good at doing this stuff. And you've demonstrated that in the work that you've done for the dissertation.
Thank you.
These are trustworthy results. I'm not going to put any deep belief in understanding the metallicity distribution function, but I do believe the metallicities that you have I'm very confident in your results. I think you've done really a lovely and outstanding job of the analysis of these spectra and have derived really interesting results and really interesting questions that will drive the field forward. This figure 5 that is still on the screen is fascinating.
Super interesting.
And well could drive the theorists crazy, I think. But more stars on it.
Driving me crazy too.
Yeah, no, it's really lovely to see. In terms of the alphas, just in general, the various different alphas, so magnesium, calcium, silicon, sometimes titanium, the formation mechanisms for those often show both metallicity and mass dependence in the yields. And since we don't know the origin of the bulge population, it's a little hard to speculate about what you might expect for the various alpha ratios. Do you have a sense from the one star that you were able to get more than one element? Do you have a sense that these are fairly consistent with our sort of normal sense of alpha elements all kind of going together? Or do you have a sense that there may be something buried, particularly seeing the silicon result, buried in the abundances when you have a larger sample that will be able to guide the chemical evolution models that are producing the bulge, the NSC in particular, stars?
So I had a very, very good look at the scandium lines, of course. I studied those again and again, over and over. And I tried to compare both the solar neighborhood stars and the galactic center stars. And if you think some people can, sometimes scandium is claimed to also be of an alpha tracer because of how it's created from alpha elements. So I don't have proper good analysis with proper abundances, as we showed earlier. But if I look at the spectra, the feature coming out from the data reduction and the size of the features and stuff like that, of course I can be blind to some temperature effects and other things. But the gut feeling is that maybe an 0.2 dex scandium enrichment, like we see with the silicon, it will not be surprising to me if that turns out to be the case, just by having a feel from the spectra themselves. Mm-hmm. So in a sense, I think so when I saw this with silicon also, it was not like, okay, it may not be correct, but on the other hand, I already had a little feeling from the scandium that something like this could come out. So it's not also something I was like, okay, we just have to not make sure that this result, there must be something wrong. We just have to believe that what comes out of the spectrum was presented, and then we'll see what we can make of it. Mm-hmm. So in a sense, I have a feeling from scandium, at least, that something like this is perhaps not completely. So with the scandium, I don't know compared to the metallicities like we see here with. So there we see also a metallicity dependence between the silicon enhancement. So I don't have that. I have not checked that feeling with the scandium if that's the same. So when I saw this, I was surprised because I wasn't thinking that there should be this kind of metallicity dependence. I was quite surprised that these actually fit so much, so almost too good. So that was a bit of surprise when this came out. This one was kind of also as shown in the spectra. If we go and look at, so we had a look at the spectra itself. Here, as I also showed in my talk, that the silicon is a bit stronger for the metal rich. So in a sense, I was ready to believe that. So I was more surprised actually to see that the other one was so similar. That this one just on top of each other.
It is an amazing result, and the models, the scenarios that you put together to explain how it could happen, I thought were very well done. They were interesting.
A lot of help from Francesca.
There are many ways to do this, but seeing an enhancement of silicon compared to the bulge seems like it might be a really important clue.
Oh, and one more thing. I actually talked to Mike Rich earlier today, and they had a seminar or a small mini conference at UCLA the other week. And the other collaboration group has done alpha for 2 stars now. And 1 star is not alpha enhanced and the other is alpha enhanced. So that's also, I'm not sure about the metallicities of the 2 stars. I didn't hear. He didn't. So I'm interested in if that fits with this as well.
Yes, you'll need to get this.
We'll see.
Yeah, that's cool. Let's see.
Breaking news.
Yeah, that's really cool. What else? Well, let's turn to the paper that I sent you.
Yes. Oh, I don't have it on this computer. You have to share it then.
Let's see. I probably have it. How do I make all this go away? Okay, here we go. Here we go. All right. So for the benefit of others, let me share screen. Can you all see that?
Yes, I see it.
Okay. So this is a paper that came out a year or so ago on asymmetric dark matter imprint on low mass main sequence stars in the Milky Way's nuclear star cluster. And I asked Brian to look over the paper and to give us a sense of what this could mean for the interpretation of his results.
Yes.
The basic conclusions of this paper are that the presence of dark matter has an effect on the evolution of the stars.
Yes.
This uses a particular dark matter model where there is some interaction between the dark matter and the baryons when the dark matter is highly concentrated, as it is in the nuclear star cluster.
Yes. So a precursor to this paper is that previously people thought, so if in the center of the star you have a gravitational well, so dark matter interacts with gravitationally, so you should expect some dark matter to be captured by the gravitation of the star and channeled into the center of the star. And in previous works, there has been this theory that maybe when these dark matters was put together in the center of the star, they will self-annihilate and produce the neutrinos that will be sent out of the stars. And in that way, you will have some energy going out of the stars, not by radiation, but by neutrinos. This, of course, has the effect that the temperature at the center of the star will go down, which will reduce the efficiency of the fusion process, which will then reduce the consumption of fuel, which will then increase the age, the lifetime of the star. So people have been building neutrino telescopes and pointing it towards the sun to see if they can catch these neutrinos. Unfortunately, they have not been able to catch these neutrinos. Unfortunately, that's a point of view. So now there's a new dark matter model based on asymmetric dark matter instead. So instead of having dark matter self-interacting and self-annihilating, they assume that, okay, we have dark matter just like normal matter with an asymmetry. So we have a lot of this dark matter that doesn't annihilate with itself, just like matter doesn't do. We don't find much antimatter today. But instead have dark matter interacting with the baryonic material in the star. But as far as I understand from this paper, the energy is not dissipated out of the star, but rather redistributed in the center. So in sense of having a very, very hot nucleus where the temperature drops off, the temperature curve gets flattened a bit, which like the other scenario has the effect that the fusion process efficiency goes down, fuel consumption goes down, lifetime goes up. But because it's flattened and redistributed further out in the star, there will be a suppression of the convective cells inside the star, meaning that for some temperature ranges, the energy will actually be better more efficiently redistributed, so the lifetime will go up. And the lifetime of the star is mapped directly in these isochrones. And in my work, I'm using isochrones for the surface temperature and all these kinds of things. So of course, it's an interesting question that if we change the isochrones, will it have an effect on the result? As been trying to think about this, I'm not really sure it will impact that much on the giants. It's interesting that the star itself would change. But if the energy is merely redistributed in the center, I'm not really sure it will have that much impact on the surface, because the surface temperature is not really depending on the core temperature, but rather the opacity of the material of the plasma of the star. And if that doesn't really change it much, the surface condition is going to be pretty much the same as far as I can see. And in that sense, I don't think it will have a major impact, at least not on this giant study. When the star becomes a giant, the atmosphere itself becomes convective further out and remixes all the material and stuff. So in a sense, yeah, I think it's an interesting idea that there will be some stars that wouldn't have had time to evolve, and they wouldn't exist then. So that will be one way to verify this theory if we can't find these stars, because they simply not have had time to reach that evolutionary process. There are some ideas that there are not as many red giants as there should be in the galactic center. So maybe this could offer an explanation to this. I don't know. That's one way. Yeah. I don't think if we connect it directly to my work, I don't think there's that much. I'm not really sure how much it will impact. Maybe a little.
Right. So it could have an impact on, for example, an age-metallicity relationship. Which
that's
would be
correct.
different for
sure.
bulge stars, and C stars in particular, not necessarily bulge stars. I think this is only likely to be a problem in the NSC itself.
Yeah. Towards the galactic center, the dark matter density will be much, much stronger than out here, of course.
Yeah. But it could mean that the stars you're observing are actually a little more massive and a little older.
Yeah.
Than basic assumptions. But as you've already noted, for the stars you're working on, it doesn't matter a whole lot once they get to be red giants. They're still sort of in the same place.
Yeah.
So.
But I think it's interesting theory to, I mean, to find these to actually observe the turn off in that amount of detail they require. I think maybe, I don't know, maybe with the new telescopes, it's a bit away in the future at the moment.
Mm-hmm. I suspect, yes, but really getting deep photometry down to look at the turnoff and at the stellar populations at the sort of turnoff range. It's an interesting way to add yet another test onto nature of dark matter and in fact its existence in the center of the Milky Way.
And getting the turn off of the stars in the nuclear star cluster will be quite interesting if we can get that down there.
Yeah, if we can get that photometry down to that level, it would be pretty cool. And even spectra down to that level would be even better.
That's where I want to go.
Yep. All right, well, I think that completes what I wanted to talk about, and I'm happy to turn the floor or the video or whatever, such as it is, back to Lund.
Thank you.
Okay, thank you very much, Kitty. I will now let the examination committee ask Brian questions. Before we do that, though, perhaps we can bring up the menti.com slide as well to remind the audience joining us on YouTube how to submit questions. Okay, so if you have questions, please go to menti.com and enter this code 7659196. Okay, and I will read your question in a little bit.
And don't forget to press the button to subscribe.
Yes, of course. All right. Okay, so with that, examination committee, you are ready. Do you know who wants to start? Or otherwise, I'll give the word to Paula then to start questioning Brian. Please go ahead.
Yes.
Hello, Paula. Nice to see you.
For me too. So, first of all, let me say that it's really a pleasure to be part of this committee, and have been impressed reading your manuscript and also listening to your presentation. So it's very interesting, and I'm happy to see the end of the work we have been discussed from time to time. So I have a couple of questions because you had already many, and one of my questions is on figure 8 of your paper 5. So where you compare the silicon over iron and metallicities of your stars with those of the nuclear disk and those of the bulge from the two works by Johnson and Bansby. And what is striking to me, even if you have been very cautious in the interpretation of all this, I will be a little less cautious, just to go a bit further in the discussion. What is striking to me is the similarity of all these.
Yes, it's interesting.
And except for possibly for the supersolar stars in the nuclear star clusters, where you see this possible enhancement in silicon over iron, you see that overall, even if the statistics is low, I agree with you, but they really seems to be on top of the Bansby et al. Data. There is some difference with the Johnson et al., but of course there are also systematics to take into account. And so my question is, in the case it will be confirmed that this nuclear star cluster and this nuclear disk have a chemical pattern similar to those of the bulge. Let's try to anticipate possible solutions. What do you think this would mean? I mean, how is it possible that on a scale, on a spatial scale as small as a few parsec, the chemical evolution has possibly be very similar to that of the overall bulge and bar? Have you thought a bit about this, and what do you think? Do you think this is something possible? Do you have any explanation for this, or I'm going too far in the future? I'm
No.
things.
No, so yeah, I can only offer speculation, of course.
Yeah.
I mean, it's kind of, I think it's kind of indicative that somehow the whole galaxy system is one system in a sense. I mean that it's not like isolated independent populations that are completely have their own life, but the whole thing is somehow interconnected in a way. I speculate. I mean, yeah. I don't really see. I mean, if originally everything came out of the same gas cloud in the beginning, it doesn't seem that far off that it will end up somewhere in the same ballpark later in the evolution, no matter where you create the stars. I mean, somehow the tracks will be somewhat similar across. So then, again, speculation. The interesting differences will probably be because of some events, merger events, or something else happening along the time somewhere in the galaxy that will cause some things to deviate a bit from what you could call the norm of the galaxy. So I mean, that's my feeling when I see this, that maybe it's all some kind of connected in a way. But the actual analysis, I mean, yeah, you will have to make very good simulations and stuff to see if you can reproduce this.
Yeah, but you are in a good place also for this. So
yes, we have some very good colleagues here doing this, and good colleagues in Paris as well.
And so this figure 8 makes me think also about figure 9, and figure 9 and 10, in fact, of the same paper. So just after that. So where you show two possible chemical tracks to explain what we see in the data and the location of the stars in this plane. And if we take, for example, figure 9, this chemical track, if I understand correctly, would suggest that the supersolar metallicity stars are older than those that have metallicities between minus 0.5 and 0. If I understand correctly the pattern, so the pattern is a kind of loop. So there is
so we have two opportunities for those stars actually.
Yeah. And I was curious to know whether you whether you tested also another scenario, maybe for some aspect also simpler than the two that you show, where in fact the chemical evolution follows the metallicity. So where you simply have a chemical evolution that is very similar to the one that we think for the bulge. And then that eventually at supersolar metallicity, you have a localized enhancement of the star formation if the enhancement in silicon over iron is confirmed. So did you test also this simpler scenario? Simpler in the sense similar, more similar to the one we think is the scenario for the overall bulge.
So if you look at figure 10, if you imagine the black line, if you push it down a bit, so I talked a lot with Emanuele Spitoni and Francesco Mattiucci about this, and they were the people who contributed to this work. But pushing this line down is not as easy as it sounds, because it has to do with the different parameters they put into these chemical evolution models. So this figure 10, it's a bit over to, so that was a bit the line of reasoning that you're saying now. I was asking if we could see some kind of signal like that. And here they have been pushing down the black line as much as they thought they could. And this stop then will then kind of show a way to get the starburst going or get star forming reignited after a quenching period. So in a sense, it was kind of an idea. Another idea I've talked to them about is, what if the infalling gas is not primordial, but metal rich? And that's also something they would like to investigate. So the idea is that Corona happened, so currently it's on hold. The idea was I should visit them for a few months and see if we can work something out that has some more model details in this, if we can find something that was interesting. I have applied for money for 2 months stay in Trieste, but it's not happening at the time.
Yeah. We should be probably patient a little bit more these days about travels and visits.
These 2 models are more an initial attempt to get started.
Yeah. Another question related to this, to the possible link between the nuclear cluster, the nuclear disk, and the bulge and the bar. In paper 1, you show the orbits, some possible orbits of your metal-proof star. And you show, for example, how these orbits can change if you take into account different values for the distance of the stars. And I was wondering, and to integrate the orbits of the stars, you use a potential where you have essentially 3 components: the massive, the supermassive black hole, the nuclear star cluster, and the nuclear disk. And I was wondering whether you think that it can be useful also to add the environment, which in this case is the bar and the bulge. Do you think that something can change in these orbits, or it's worth trying to develop some new models taking into account also the overall potential of the bulge or the bar? Or do you think that for these stars that are so close to the galactic center, the bulge bar environment is not really essential to understand and to model the orbits?
So I have to be clear that I didn't actually do this modeling. It was Tobias Fritz, but we have discussed it a bit, and the potential. So we have some proper motions from Symphony. So that's the fortunate part of being so close to the supermassive black hole, that there are so many observations of all kinds of stuff, and radial velocity measurements as well. So we're trying to kind of figure out where the orbits are heading, but mapping the gravitational potential is of course important to actually say what kind of membership these stars are. And these stars, so I don't know how important it will be to do the bar and the bulge for these for these calculations. Those stars that we say are in the nuclear stellar disk are very, very close to the nuclear star cluster. So because they are so close, actually it becomes a bit important, but also a bit difficult, because there is to some extent also some mixing. And in the end, is the star really the nuclear star cluster, nuclear stellar disk, if it's in the borderline, in the gray zone, in between? And I think for those, if we want to be more clear on those, we will probably need some better models of the gravitational potential in the region. But I'm not really sure how much more we actually need. We also need better proper motions and stuff like that. So I don't think we're that much in trouble with the current modeling.
Okay, good. And very last question from my side. You were talking before about your wish list, and
Yes.
would it be possible in the future, for example, for the nuclear star cluster, to have access also to abundances like sodium or aluminum, to try to look at anticorrelations and see if we really can end up with some robust conclusions about the origin of the nuclear star cluster and how much of the nuclear star cluster comes from dissolved globular clusters. Can you say something about that? Do you have plans about this, or is it difficult?
Yeah, we really want to do the anticorrelations. It's an obvious thing to do, but we don't have the abundances to do it. So that's definitely on the wish list, because that will be very. It will go straight into the discussion on whether or not we have globular cluster info or not. So that's an obvious thing to look for. Whether or not I think we have I think it's a mix. We probably have these 5-7% also as Twandu and our claims. I don't think would be a mystery if that turns out to be the case. I think that would be quite reasonable. In Heidelberg 2 years ago, we called it the Italian population. But yeah, I think it will be reasonable to expect that to happen. But it will be very nice to have these anticorrelations for sure. So that is on the wish list. And I think we have an aluminium line, but it's too strong for us to dare say. But we would also like oxygen. Yeah.
Okay, thanks. Well, it's all on my side. Thank you very much for answering.
Thank you.
Okay, so next person in the examination committee to ask questions, I suggest Magnus.
Okay, thank you. So thank you very much for this thesis and the presentation. I enjoyed it a lot. And as someone coming from a bit of a different field, I certainly know much more about our galactic center now than I did before I read this. Thank you so much. So I, as maybe you know, I study black holes quite a bit. So of course I'm very interested in the black hole in the galactic center. And one thing you say in the beginning of your thesis that nuclear star clusters are more common than supermassive black holes in other galaxies. And do you think this is because there actually are fewer supermassive black holes, or just that they're more difficult to find, so we don't see them?
I think a large reason for that result is so far as we're not as able to detect them. So I think a detection issue is I think whether or not we actually can confirm or deny the existence of the supermassive black hole is still an issue, I think. And then, of course, a good question would be what happens if you have two galaxies colliding and stuff like that. Would that have an impact on whether a supermassive black hole stays in the merged version or not? I can't really say. I don't know. It could have some. There could be something to that discussion. But I think mostly, I probably think we'll find more of them when we become better at detecting them.
So would you expect to see any sort of signs of the activity of, say, let's look at the Milky Way, Sagittarius A star. Like, would the black hole accretion effect give different results for your studies? Or will your studies be able to tell us more about the activity of the Sagittarius A star?
So one thing I've been speculating, this is also speculation only, is of course the tidal force of the supermassive black hole is quite immense, and one of the stellar evolution tracks that are important in this is the supernova type 1a, which require a binary system, a white dwarf with mass transfer. But what if this binary is close enough to the supermassive black hole to be tidally disrupted? Would that then mean a suppression of supernova type 1a? So we have some good cosmologists here in Lund, and they say maybe inside a few parsecs it might be a thing to look at. but it's pure speculation. I'm not really sure if we can actually get a result like that, but it could be one way that supermassive black hole actually could have an impact on the evolution track of the stars in the nuclear star cluster. I think that would be, could be interesting to figure out. Maybe this light abundance, overabundance could be a signal of that. I don't know. A speculation. Something to
it sounds like
a lot of fun things to look at.
And so I also tried to sort of put your results in the context of other wavelengths. So one of the big discoveries that I've been looking at in the past few years are the Fermi bubbles, of course.
Yes.
These huge structures that we suddenly discovered. So as you might know, there are different origins suggested. One is, of course, an accretion event in the supermassive black hole, but another one that I saw is that we suddenly had a burst of supernovae going off in the galactic center, and that would then give the energy. Would you care to comment on this based on your results?
So there could be some kind. We have no idea why the alpha enrichment's happening in the metal-rich stars. I mean, there could be somehow a metal alpha. There could be a lot of supernovas type 2A going on and enriching the alpha for the metal-rich stars. But on the other hand, there was also there will be a lot of winds and star formation suppression and stuff going on. I think I'm not really sure if I can connect them directly to my result, but. I think definitely. I mean, if you take the evolution track with a stop in star formation, you could argue that maybe AGN feedback or something like that created the Fermi bubbles was also responsible for the stop in the star formation. So in that sense, they could be connected in that way, perhaps. But that, speculation.
So,
but I think it could be interesting to. It would be I mean, it could be interesting to see if we can get a timeline for the AGN feedback for the Fermi bubbles. Where and when were they created? When did they stop? But I'm not sure people even know that. But if that was possible,
well, I've seen a number of guesses. I think the last one I saw was 5 mega years or something like this. But it's a big range. But definitely something to look into. And I think, these two scenarios would give very different effects on the galactic center. So, with studies like yours, and as you continue and learn more and more, maybe
my study can help setting constraints on that.
Yeah, exactly. Then just another small thing that I noticed in introduction to paper 3, you say that high extinction at present restricts investigations to the infrared. I'm just wondering, are you expecting this to change? New techniques, new knowledge or something? Or...
Oh, so with a bigger telescope, we will have more photons, but it will still, I don't think we'll ever get to the optical, no matter how big telescopes we build. But if we build a bigger telescope, we can actually go closer towards the optical wavelength regime. So we have been investigated out in the K-band, so 2 to 2.4 microns. But if we can go into the next window in the H-band, a lot of the H-band has been really well developed over the last couple of years because of the Apogee survey and iGRINS and other stuff are doing a lot in the H-band. So if we can build bigger telescopes, we might be able to do H-band observations of the galactic center, and that will open up for a lot more spectral lines of more species than we have available in the K-band. And together with that, I think we can do a much better abundance analysis. That will be really interesting. So I'm really looking forward to what these big telescopes can offer us.
Yes, I think many of us are.
There must be a lot of competition on the time, I guess.
Yes, of course. And then I just had a question also about, because you've sort of done in-depth studies of one star or a few stars, like a small sample, and you say a few times that, you are limited by the sample size. And then at the same time, we know that there are these big studies with, hundreds or thousands of stars as well. Could you care to, comment on these two? What is the advantage of one versus the other, or something like that?
So we need the big studies for the statistics. but the big studies require more time to analyze. So when we have hundreds of thousands of stars, or even millions and billions, we'll need techniques that can map these more time efficiently than we could do manually, of course. But then again, surveys don't have the same focus that the manual observations have. So we can sit for an hour and expose one star and get a very high signal to noise. And also we can go up in higher resolutions than the surveys can. When you have high resolutions, you need more photons to fill the bins. And with the higher resolutions, I mean, when you do a machine learning technique, it will find signals that you're looking for. So you kind of need to know a bit about what you're looking for. You have to train your training set, and you have to build it and make sure that it covers the signals that you want to find. But if you want to find a new signal, what then? Sometimes you can do it in outliers in the machine learning result. But if you really want to find the new signals, you have to focus in on a few stars and look very carefully. And this is where I see the interplay between what we're doing and what the surveys are doing, that we're trying to make very, very careful analysis of few stars and maybe point the way to where we should be looking. And then the machine learning people can kind of see, okay, some people are saying this is a possibility. Let's make sure that we can discover such signals. And in the end, I mean, they will play back to us and say, but we're not finding any of this, but we're finding some outliers here, and we can learn from that and focus our investigations also. So I think, in a sense, there's a nice interplay between the two approaches, and I hope it continues.
Yeah, I really agree. I think, it's often the serendipitous discoveries, or like there's one thing that doesn't quite fit that we learn a lot from in the end.
Yes.
So then we really need to do these single in-depth studies to learn what we can.
Exactly.
So I wanted to ask you finally just some personal sort of questions, like what do you consider to be the greatest achievement, or what are you most proud of in the results that you present?
That is the alpha study in the end. But also, as Katie nicely put it, the advocacy of paper 4, that we need more atomic physics. So those two results.
Yeah, no, I totally agree about the atomic physics. Also in high resolution X-ray spectroscopy, then we really also need to be informed by atomic physicists. So I completely agree. This is super important.
I hope some funders are watching this.
And finally, if you could pick just one more question or one thing that you could focus all your energy on, what would it be?
That will be so I really like spectroscopy. So I really want to do a more detailed spectroscopy of everything, and then a slightly different topic I could just do a spectroscopy on is exoplanet atmospheres. But the exoplanet atmosphere models are way, way, way underdeveloped at the moment. So it's really difficult to do anything but detections. But that's a future avenue that could also be interesting. But in order to do that, you will need to do the host stars. So we have some promising students looking into that.
Sounds good. I'm looking forward to hearing the results. Okay, that's all the questions I had. So thank you.
Thank you.
Okay, thank you very much, Magnus. Then I'll give the word to Alejandra to ask Brian questions.
Hello.
Hello, Alejandra.
Hello, Brian. Happy to see you.
You too.
Congratulations for all the work that you have accomplished. It has been careful and important work. I have particularly appreciated, in fact, this how thoroughly, how rigorously you have performed your abundance analysis, considering all the possible pitfalls of chemical abundance estimations, and there are so many, the atomic data, the population biases, the molecular line blends, etc. And you have carefully considered all of them without neglecting any possible source of bias, of errors, not putting anything behind a carpet. I think this is really very important. It's an example, especially in the era of these big spectroscopic surveys that, as you said before, have the tendency of being less precise, less attached to all these small questions that are, in any case, so important and can change so much in finally robustness of the results. So I think that, yeah, the work that the one that you have performed has to be is an example for all these spectroscopic surveys that shouldn't renounce to achieve the same kind of robustness. Yeah.
Thank you.
I have just 3 small questions because I'm the last one. I imagine that you're starting to be tired at this point.
Time flies very fast at the moment.
Okay, so yes, I have a first small question about your analysis procedure regarding the gravities, the gravity estimator. So I understand that, well, getting spectroscopic gravities was impossible at that point. So I really appreciate this second procedure that you have used. But I was wondering if you have checked the agreement between your spectroscopic temperatures and the isochron effective temperatures, because sometimes there are some biases. It's typical because maybe we are considered different ways of estimating the effective temperature. And as you then projected those isochrons to get in the gravity, have you checked that you were on the same scale with some kinds of calibrators? Or?
So we did both the photometry and the isochron method and listed both. So we did that in paper 2. In paper 3, we only did paper 5. We only did the isochron method, and there are some differences between the log Gs. So we felt we had to use one or the other. But some of the stars are in agreement. That's nice, but others are not. And of course, I mean, what is the impact exactly on if you have 0.35 log G difference? So in the end, we said, okay, the extension is simply too patchy. There's too much problems with the photometry, so we don't dare use it. But we did try to see actually how it performed compared to the isochrons. But we were getting too far off the isochrons. We didn't dare to use it.
Okay, thank you. And then I have a more general question. So if, let's imagine that in the future you could perform high resolution spectroscopy of the galactic center to get any chemical abundance, but you had to choose 2, let's say 2. What chemical elements would you choose? What do you think are the most promising chemical diagnostics for the galactic center?
I would choose 3.
Yes.
C, N, and O.
Okay. And why?
Because for the first, the molecular molecules are so important, especially when we go up, especially in the metal-rich stars, on which we have a lot of metal-rich stars. So in these metal-rich stars, we have so many spectral features that we really want to make sure we have a grasp on at least the molecular blendings. And C and O are also kind of fundamental. I mean, there are, and O could be an alpha tracer. So, I mean, I think those are the 3 I'm most concerned about when I do abundance analysis.
Thank you. And my last question concerns the possibility of getting dynamical data for those stars, because you know that coupling chemical diagnostics with dynamical ones is a powerful tool for understanding the evolution of stellar populations. So how do you see the perspectives regarding astrometric data in particular for stars in the galactic center? I understand that it's difficult, but how do you see the framework today and in the future?
So there's a lot of kinematics very close to the black hole, and I hope that will expand further out and include the full nuclear star cluster and nuclear stellar disk. I think the nuclear stellar disk was with a mass of 100 times the nuclear star cluster is going to be very important. But the kinematics is not really out in including the nuclear stellar disk. So I would like to see that happen. And of course, that also means that should be time series observations of the nuclear stellar disk going on. And that will be expensive because it's the galactic center, but it will be very appreciated if it happens at some point.
Okay. Thank you very much. Thank you very much.
Thank
Okay.
you.
Then I will move to questions from the audience, and I will begin with the audience present in the room. Microphones, do we have this to... Yes, okay. So first of all, do we have any questions for Brian? I have one up there. Should I...
Microphone.
Yes.
So following up on the last question, do you think that the Gaia infrared will be very beneficial?
The what?
The Gaia in infrared.
Infrared.
Sorry, Greg, can you repeat? I don't think the YouTube audience heard your question, but maybe now. Okay.
So do you think that, given the last question, that the Gaia infrared, so the future, let's say Gaia potential mission, would be beneficial for the kinematical study of the stars that you're looking at?
I actually don't know if it penetrates all the way into the center, but if it does, I would love it. But Gaia infrared does penetrate through dust, so it's definitely a right step in the direction for this. I'm not sure how low magnitudes it will be able to reach into the galactic center. We could ask one of the proposers. 2 seconds, Dave.
It aims to go to 20th magnitude roughly in H and K band, but these things have not been fixed in stone yet. So
we would like to request that you are able to capture the galactic center.
Yeah, I mean, one of the problems with such a survey is the crowding, of course.
Yes,
and
it's extreme.
The deeper we go, the problem is that we get too much data, so we may not be able to get everything.
Okay, are there any further questions from the audience? I have received a telegram from the interwebs.
Okay.
So let me read that for you now. How does the range of CN band strength values that you see in the nuclear star cluster stars compare to the range seen in globular cluster giants? And can this help us understand the history of the nuclear star cluster? In case you want to see the question, I will give it to you here.
I haven't observed globular cluster stars with respect to CN bands, so I actually don't know what they look like compared to the nuclear star cluster. But if it turns out that the CN bands in globular cluster has a similar overabundance or a signature to nuclear star cluster, that will be an important diagnostics to compare with, of course. Mm-hmm. But at the moment, I have no clue about that.
Okay. So if there are no further... we have a further question from Henrik.
Okay, so it's a follow-up question on Alexandra's questions. If you could choose 2 favorite elements that you would get data for, which one would it be?
Atomic data.
Yes.
So yttrium. And then the strong lines we have, the magnesium, calcium, and stuff like that. Make sure that all of that is mapped into infrared. Particularly, I would like collision cross sections. If you can supply that for these elements.
Okay, so I believe we have no more questions. So before I close the Defense Act, I would like to thank, first of all, the examination committee, Magnus Axelsson, Paolo Di Matteo, Alejandra Recio Blanco, the faculty opponents, Kitty Pilakovsky, and also you, Brian. Thank you very much for the effort. So, yeah, thank you. And now,
thank you so much for the nice questions.
Yeah. Okay, so I will now close the open part of the Defense Act, and the examination committee will remain online for the closed part. Okay.
Okay.
Thank you.
So